Hi. In the previous video, we were solving systems of simultaneous equations by matrix inversion. Now, we're going to do the very same thing, but using the Cramer scheme. Look, I understand that this process of solving a system of simultaneous equations using matrix inversion is a little bit complicated. So why not simplify this a little bit? Okay, so look, we've established that vector of solutions x is given as inverted matrix A times D. Vector D, vector of constant terms. Or we could write that this is 1 over the determinant times adjoint A times D. But of course, adjoint A is nothing more than transposed matrix of cofactors, right? So let's use those two corner expressions to see if maybe we can make everything simple. Okay, so look, vector x is in other words vector of values of x. Oh, I'm sorry, n that we are trying to find, and it is equal to 1 over the determinant of matrix of coefficients, so matrix A, times matrix of cofactors. Matrix of cofactors is given by transposed matrix of cofactors is given by C1, 1. Then remember, here we have C1, 2, not like usually, right? Because this is a transposed matrix. We've discussed this 2 videos ago. And here we would have C1n, right? Here we would have C2, 1, C2, 2, until C2n. And we go on like this until we would get Cn1, Cn2, until Cnn. Okay, and then we need to multiply this inverted matrix A by vector D, right? So vector D will be D1, D2, until some Dn. Okay, so if we're gonna multiply this out, what we're going to get is C11 D1. This will be element over here, plus C21 D2 plus Cn1 D. Right? Remember, this is nothing new over here. We are just multiplying in every row by one single column that we've got here. And by the same token, here we would have C21 D1 plus C22 D2 plus Cn2 D. And of course, we would be going like this until we would end up in the last row, which would be given by C and 1 D1 plus C and 2 D2 plus C and D. Okay, and look, now we know that actually in order to obtain the solution, what I need to have? in order to obtain solution for x1, I just need to take this expression and divide it by determinant A. Okay, let's rewrite it a couple times. So, x1 is given by C11 D1 plus C21 D2 plus Cn1 Dn divided by determinant of A. Okay, now we can get that x2, the solution, will be given by C21 D1 C22 D2 plus until Cn2 Dn. Of course, this is divided by the determinant. And finally, x with asterisk n, okay, hope I'm gonna fit it all here, is Cn1 D1 plus Cn2 D2 until Cnn Dn. Okay, now again, I could take this expression and quite easily rewrite it using the sum symbol, right? Okay, I'm gonna do it a little bit lower. And so how will it look over here? x1 would be equal to, we start with the sum symbol, and what repeats over here? Well, we see definitely that we will have cofactors, again, and expression with d. Now, each cofactor here has the second index equal to 1. The only one thing that changes is actually the row in both the cofactor and in elements of vector d. So we got I equals 1 over n. And this divided by the determinant. Okay, now we can do the same thing for x2. And we will have that this is sum ci, this time 2, di. Equals 1 divided by the determinant. Then we will go on like this until we arrive at xn, and we would have 1 Cin di divided by the determinant. Okay, look, every time when we've been dealing with expression with cofactors like this, we had it had something to do with Laplace expansion. Remember, when we were deriving the expression for inverted matrix A, we used regular Laplace expansion and Laplace expansion with alien cofactors. But look, here the situation is a little bit different, right? Because here, before, we had some A over here. So some element from matrix of the coefficients. Now we've got this d, and this is very problematic unless we can somehow connect these two. Because look, if I want to make a Laplace expansion by, well, definitely by alien cofactors, then I would use, for example, cofactors from row, from column, let's just say, Because now, remember, we are in one column and we are moving along the rows, right? Because I denotes row. And the same is here. Of course, it makes perfect sense because D is a vector, right? So it has just one column, and we are getting lower and lower and lower within this vector. Okay, so let's see if we can connect those. Remember, those are the cofactors from matrix of coefficients. Okay, so what could we do to have, let's just say, this original matrix of coefficients changed in its something to get expression like this? Okay, let's try from the beginning. So look, our matrix A is A11, A12 until A1. A21 until AN1. A12 until A1N. A22 until A2N. And of course here AN2, AN. Okay, so if I would like to make Laplace expansion of this matrix, how would I do it? For example, I could choose the first row, right? And what would I do then? Well, I would take element A11 and I would multiply it by cofactor C11. Then I would add element A21 and I would multiply it by cofactor C21. Then I would be going like this until I would arrive at element N1 and I would multiply it by cofactor Cn1. And of course now I could do this. I could write this using the sum symbol as n I equals to 1 I 1 C I 1, right? Okay, but this expression is clearly different than this. This is just expression for the determinant. So what would I need to change in this determinant to go from this expression to this expression, right? Because we are clearly connecting this to variable x1. Why? Because look, 1 is the repeating thing. What is the thing that is different? Look, here we just have A11, A21, AN1. Look, what if I took vector of constant terms and I would place it over here? How would our formulation change? Look, the minor change is that this is a vector, so it doesn't have two subscripts. But this is not a problem, because look, this subscript, when we were doing the expansion by the column, was frozen anyway. It was always 1. And look, if I would just take this vector and replace the first column, what would I have over here? D1, C11, D2, C22, Dn. C21, Dn, Cn1. And look, here, now, I would have di, which means that now this would be equal to x1. Okay, maybe we're onto something. Okay, so will this work for element number 2? No. Okay, let's try again. If I'm going to do Laplace expansion, now, okay, if I'm going to do Laplace expansion, now for the second column, what am I going to get? Well, using Laplace expansion, we are going along this column, so we get A, 1, 2, times C, 1, 2, plus A, 2, 2, C, 2, 2, plus until A, N, 2, C, N, 2, which of course can be summarized in the sum symbol as A, I, 2, C, I, 2. Now, what should I do to get, what should I do over here to get an appropriate result? Because I want to transform now this expression into this one. How would I do it? Maybe we're going to use the same trick. What if I replace this column with vector of constant terms? d1, d2, dn. Well, what will happen over here? We will have d1, d2, dn, di. Again, this is equal to x2 with asterisk. So we got a second solution. Okay, let's go further. Let's check what would we have to do to get the last element. Again, now let's just say that I'm going to perform Laplace expansion with respect to last column. Okay, this will be A1n C1n plus A2n C2n, right? Plus until A N N C N N. Again, I can write it in the form of some symbol as A1N C I'm sorry, C-I-N C-I-N, right? Because only the first subscript is changing. So again, let's use the same trick. And the trick here is very simple, right? D1, D2 until Dn. What is now changing? We've got D1, we've got D2, we've got Dn, we've got Dn here, which gives us the last solution. And this is actually the trick. This is the trick. Of course, I forgot in each case, we would have to get this, we would have to also divide by determinant alpha. But this will become apparent in a second. Okay, so in general, what do we have over here? Look, if I have some matrix A, maybe, no, let's start different. Look, we can say that if we've got some x's, and let's just say that we've got we want to find some x m or xk, maybe it will not collide with any of the notations that we had before. Look, xk, in order to obtain it, we would have to calculate a special determinant that we would call ak, and of course divide it by the original determinant a. Right? So, how do we do? Look, here we would have a11, a21, until an1, a1, 2, a2, 2, to an2. And then we would end up in some column k, and what would we do in this column k? We would just substitute this vector d1, d2 until dn. Of course here a1n, a1, a2n, a-n-n. And this is the entire trick. Look, I know that this must be a little bit confusing at the moment, but once I'm going to show you the example of how to do it, you will understand that this task is just extremely easy. Okay, so look, what have we learned? Basically, we've derived formulas for these solutions. Look, we derived them directly from matrix inversion. I just used the solution obtained by matrix inversion, right? To obtain each of those. Then we discovered that we can get those expressions that are in the numerator over here, and over here, simply by replacing the consecutive columns by vector of constant terms d, right? And the only thing left to do is to divide those by the determinant. Something I forgot along the way. I'm sorry. Remember, of course, each of those needs to be divided by the determinant. But actually, that wasn't the main focus of what I was trying to tell you. Okay. So, this is it. This is how the Cramer rules work. This is how you derive it. And in the next video, I'm going to show you examples. And as you will see, actually using Cramer's rule, even though it might look very confusing at the moment, is way easier than using matrix inversion. But as I said before, you need to know both. Okay, thank you and see you in the next video.